Alright guys, so here we are taking a look at these notes on graphing our geometric or exponential equations. Okay. Now, as you noticed, probably right here, you can see my table had some issues. I was apparently trying to erase it and couldn't undo that, so I had to write it in here. I've also previously made this video, but I didn't turn on my microphone, so this is my second go-round, so hopefully I don't forget anything I did the first time, but that we'll be able to get the information we need so that you guys know how to graph these geometric, these exponential equations, okay? Or tables or relationships, whatever you want to call them. First things we need to remind ourselves about is that we are going to have discrete and continuous situations, okay? Discrete, remember, is finite, meaning it doesn't just keep going, okay? It could in one direction, but generally it doesn't. Also that there's no line, okay? The parts in between, they're not part of the solution, so we don't draw the lines, we don't connect the dots. Whereas continuous is infinite, generally it's going in both directions forever, and there is a line, meaning that every part in between the points we actually graph are solutions to the problems, okay? Generally, when we're looking out for them, okay, discrete, we see that sequence notation at a sub n, whereas continuous is usually y equals, and we have an x in there as well, okay? Also, the context of the story problem determines that as well, because if it's a problem that talks about it being continuous, then it's going to be continuous. You know, for example, let's say we talk about hair growing, right? The way hair grows is continuous, right? It's constantly growing out of our heads in every direction. Okay? So that would be continuous, right? Now, when you go and get haircuts, that would be more discrete, right? Because you're cutting off a piece at a time, right? So we're cutting off a chunk of hair. We're not like continually just snipping away at the hair. So if you have that context, that's definitely going to affect what it is that you, whether it's discrete or continuous, okay? But for us, when we're dealing with just equations, we're generally looking for the x and the y, or the a sub n, to tell the difference. So in this, our two tables are both x's and y's, so we're going to be continuous here, okay? So we just plot the points. So negative 2 1/3 would be about right there. Negative 1 1 right here. 0 3 right there. Right, these are just the points. 1 9 right up here. And 2 27, which would be probably up here above our graph and above the words. Okay, and we can see we're timesing by 3, aren't we? And we started at 3, so if we were to do the equation, it'd be 3 times 3 to the x. Okay, because it's continuous, we're going to want to connect the dots, right? Now, something we need to understand about these, okay, is the fact that we have, well, let me just start by doing this. Okay, so we draw our points right there, right? Okay, now let's look at number 2. So negative 264 is going to be hard for us to draw because we can't go up that high. However, negative 116 we can. 0 4 1 1 and 2 1/4. Okay, so we can definitely see that we are timesing by a fourth, or in other words, dividing by 4 each time. Okay, so it'd be like 4 times 1/4 to the x if we were making our equation. Now, the problem is, if we try to draw this, sometimes people will make the mistake of just kind of going down in that same direction, and that is not correct. Okay, that is not how it works. And let me show you, and we can use, it should actually go like this. We can use Desmos to help us do that. So let's pull up Desmos here, and let's type in that equation. Y equals 4 times 1/4, and we should probably put this in parentheses, to the x, okay? Now, let me also do this. Okay, so we've got this same situation going on here. So A was 4. B was 1/4. So about 0.25, which looks like it may not let me go there. There we go. Okay, so we can see we've got that same graph here. Now, if we zoom in, we should recognize that as this graph is continuing on this path here, it's getting closer and closer to that x-axis. Okay, well, that x-axis has a name. Okay, it is our asymptote. Okay, and with the asymptote, what it is it's, we'll do the dashed lines. I like the dashed ones better. It's basically an invisible line that our line is never going to cross. Okay, and it doesn't matter if we adjust these. Okay, we can still see that no matter what we're timesing by, no matter what we're starting as, okay, our equation is still going to be in one direction or the other, going towards that asymptote, that invisible line. Okay, and the idea here kind of stems this way. We can use this divide by 4. So let's say we've got a piece of paper here. Okay, and we're going to cut it into fourths. When we times by 1/4 or divide by 4, we basically get rid of the 3 other pieces and we're left with 1 piece, aren't we? Okay, well, we can keep doing this, can't we? Just like our pattern shows, we can keep taking the piece that's left over and cutting it into fourths. But what do we notice about that? And I'm going to run out of space to be able to keep doing that. What we should notice is we always have 1 piece of 4 left over. So we never get to 0. Okay, we're never going to have it all disappear. So that asymptote represents that 0 line in this case, and the fact that we're never going to get there. Okay, same way if we think in terms of this. If we were going backwards, we'd be dividing by 3. Okay, so what that gives us is it gives us this line, this asymptote, which is basically an invisible barrier that our equation is never going to cross. Our line is never going to cross. And generally speaking, it is where x equals 0. Okay, that unless we have any shifts up or down. Okay, like in this case, say we added c to this. Okay, so if I added a c there, see how that shifts my graph up or down? It also shifts that asymptote. We can see that it moves it, and again, it looks like it's gonna touch it, but if we zoom in, we can see that it actually isn't touching. Okay, because that's just the nature of how our exponential equations work. Okay. So that's kind of a great way that we can pay attention to what is happening, and we can look at that information. Okay, so when we're graphing, we need to understand that idea of the asymptote, because that'll tell us kind of how our line is just going to basically flatten out. We also need to know where it starts and how it grows. Okay, and that's the basics of graphing these exponentials. Whoa, that's kind of weird. Usually the whole thing moves. Anyway, oh, there's a lot of different layers apparently right here now. Okay, so let's keep going on. So now, when we're graphing these recursive, okay, we've got the a sub n here, so we know these are going to be discrete, which means no line, okay, because the points in between aren't part of our solution. So we find where we start. A sub 0 equals 1, there's our y-intercept. We're times them by 2, so every time I times by 2, I'm going to go to the right one, okay? Because if we were to make a table here, it would look like this, wouldn't it? It'd be growing by timesing by 2. But this left side, the x side, okay, is only going up by 1. So that going up by 1 is we see in that horizontal movement, whereas the y value timesing by 2 we see as we move to the next point. So 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Okay? And really, that's all I do. Because it's discrete, I just need my points. Now, if it were continuous, right, we'd have this drawing right there, which would mean that every single point here on this line would be part of our solutions. Okay? But because it isn't, we only have to draw the dots. And I don't know if you heard that clomping, but it sounded like somebody is up on the roof above my classroom. So, fun stuff. Okay, so again, we just needed those points. Okay, now, if we really wanted to, we could go this direction and kind of do the opposite of dividing by 2, but we don't necessarily have to. Okay, number 4. So now we start at 2. This time we're timesing by 3. If I move to the right one, I go 2 times 3, which is 6. 6 times 3, which is 18. 18 times 3 would get us clear up there. This one may look like you need a little bit more numbers, dots, to show you. So I could go back and divide by 3 and end up looking like that. Okay, that's kind of up to you. But again, they're discrete, so we don't draw the lines. All right? Okay. Now looking at number 5 and 6, again we see that notation, the a sub n, so it's sequence notation. These are actually explicit equations though, not recursive. Okay, but it's in that format of a times b, so a being our y-intercept, our start, b being that growth factor, what we're timesing by, that rate of change. Okay, so at 3, go up to my y-intercept, and 3, timesing by 2. Again, as I move to the right one, I times by 2. So 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. And we're good. Okay, again, though, I could move backwards if I really wanted to. 3 divided by 2 would be 1.5, and down here-ish. Okay, but I don't necessarily have to. But, again, it's discrete because of that sequence notation, so I'm just going to leave it like that, which I know can seem very incomplete at times. Okay, number 6, again, starting with 4, so we go to 4. Now we're timesing by 1/2. So you got to remember, when we're timesing by 1/2, that's the same as dividing by 2, right? Because the reciprocal of timesing is dividing. The reciprocal of 1/2 would be 2 over 1, or just 2. So you can think of that way if you'd like to, just like timesing by 1/3 is the same as dividing by 3, timesing by 1/4 the same as dividing by 4, timesing by 2/3 same as dividing by 3/2. Okay, so you get the gist. So on these ones, generally it's a good idea though to do the left side as well as the right side of the y-axis. So timesing by 1/2, we'd cut it in half to go down to 2. 2 times 1/2 would be 1. 1 times 1/2, and 1/4, and so on. But now we can see where it should look more like this. We see that instead, we're just getting that part of it. Okay. By the way, something I forgot to mention. Well, let's finish this one first. So we go backwards. We would times by 2. So 4 times 2 would be 8, because 8 divided by 2 would be 4, and then it would be 16. So we'd go to the left one at a time, and now we can see that better picture. Okay. So yeah, there we go on that one. Now, whether it's discrete or continuous, when we go left to right and it's going down like that, that's what we call exponential decay, when it's getting smaller, okay? Whether it's discrete or continuous, if we're going up as we look left to right, that's called the growth, exponential growth, okay? So that's just some words we often use to refer to those as well, which I failed to mention earlier, so I thought I'd do that right now. Okay? All right. So let's take a look at these last ones now. Okay? So we've got 2 times 4 to the x, and now we've got y and x, so these are going to be continuous. So we start at 2, we're times them by 4, still I go to the right one. 2 times 4 is 8, 8 times 4 is 32, which is going to be clear up there. Going backwards, 2 divided by 4 would be 1/2. Okay, and because there's no vertical shift, I'm assuming that's a asymptote there. So I'm going to just kind of shoot this up like that. Okay, and that's all there is to it. For number 8, same idea. Start at 3. This time we're timesing by a third, so that's like dividing by 3, right? Let's actually write that off here, dividing by 3. So as I move to the right one, I divide by 3 to get 1, then 1/3. Again, I'm assuming that asymptote is right here. Okay, so I'm going to want to go backwards, right? So I'm going to want to times by 3 instead. 3 times 3 would be 9, so when I go back 1, we multiply by 3, and then it would be 27, which would be like up here. So it'd go something like this and get really close to that asymptote. Okay, and that's all you got to do when it's that pretty simple stuff. Now, let's think, what if we actually did have that vertical shift? Okay, say we added 3 right here, or subtracted 1. Okay, well, basically all that is doing is shifting everything up 3. So my asymptote shifts up 3, and so do all my points. Okay, and it would look kind of like a parallel. It's kind of hard to draw that really great though. But that's all that it's really doing, okay? Now the interesting part here to me is that, notice from the asymptote, my distances are going to be the same, okay? So even if I'm using this different color, okay, that it's shifted, my asymptotes, the distance from the point to the asymptote is going to be the same on each of these, okay? Because it's just like we're shifting the whole thing either up or down. Plus would be up, minus would be down, okay? The weird thing is when we make our tables, it's hard to see the difference, okay? So like this would be -1, 1/2, 0, 2, 1, 8, 2, 32. Whereas our blue one that got shifted would look like this. 3.5, 5, 11, and then if we got to it, it'd be 35. So what we see is that +3, we see in those y values that we're adding 3, okay? Now what's weird is if we're just given the table, it's easy to see that this is timesing by 4. This, we can't see that times by 4 there, can we? Okay, because of how all the numbers have been shifted up 3. So that's kind of the really weird part about it, but when you see something like that, just recognize, hey, we've just got to take something and shift it up, okay? Again, if we're looking at Desmos to do this, okay, let's give ourselves an easier problem to look at. Say we've got our original function is 2 times 3 to the x, okay? Well, let's make this match. So 2, 3, okay? So we can see here, right? That's our original. So that C, if I'm adding those numbers, notice that the whole thing again is just kind of shifting up from that, okay? Or if it were negative, shifting down. But from the asymptote, it's still the same distance, okay? So like say I go down to -4, the distance of, and I don't really have a pointer here, but the distance from this point right here to the origin 0, 0 is the same as this distance from apparently can't. Oops, didn't want that. From that point to that point. Okay, so that A is still the same. It's just been moved. The whole thing's been moved around. Okay, so that's just kind of something to pay attention to. Same with this one. If we're subtracting one, all these points basically just shift down one. Okay, which seems pretty simple when you're actually doing it. And so the asymptote shifts down, and then my graph would shift down one as well. So my suggestion, if you ever see that +3, that -1, that addition right there, graph this thing, or at least write the table to it, then apply the -1 to everything, or the +3 to everything, and then draw your new graph. That's probably going to be your best bet. Okay? All right, guys, so there we go.